Planck's constant. Hey, we're back. Okay. Okay. I know there's an example problem there. We'll do that in just 1 second. But if this is the whole payoff, finally using waves for something, right? Energy is kind of where we're going. We know that energy, high, low energy, contains the waves, wavelength, frequency, all that kind of stuff. And if you notice, based on the equation, frequency is responsible for energy. But we know wavelength is connected to frequency. So it's kind of an A to B to C type thing. But we'll get there. So something to point out for Planck's constant. Okay. Kind of funky. So this is one way that we derive units, especially with constants. So watch this. Okay. So we know that frequency is in inverse seconds. Okay. Energy is in joules. We don't know what H is yet. Okay. But 1 over seconds is kind of like 1 over 2, 1 over 50. If I want to get rid of that seconds, I can times both sides by seconds. If I do that, that lets us know the official units for Planck's constant, which are, well, here you go. Units for Planck's constant are joules seconds. That's not joules per second. That's not joules inverse seconds. Joule seconds. Constants have this funkiness where the units don't have to make sense because the number was solved for. It's calculated. Basically, the units do whatever the problem needs it to do. So if you feed the problem joules, the units need to kick out frequency. If you feed it frequency, they need to give back joules. So there we go. We should just start the equation. Okay, here's the nice thing. The equation is built to give you energy. So when it says how much energy, that's great. You're just solving for E. Let it do what it do. Okay. So Planck's constant, just like speed of light, I'm going to have to give you Planck's constant. But there we go. So there's 6.626 times 10 to the negative 34. Crazy, but hey, that's what it is. Joules are tiny. You know how we say RDA is 2,000 calories per day? Those are actually kilocalories, so it's 2 million calories per day. And then a joule is slightly more than 4 times that. So you're eating like 8 million joules a day. So just realize that these numbers, they get big really, really fast. I still need times by the frequency. Frequency is 2 times 10 to the 4th. Kind of weird with having such giant numbers and then it's just a 4th. But here's the crazy thing. This is the highest frequency we can hear before it starts to damage your hearing. We're not even talking how loud. This is just frequency. But that also is like, oh shoot, that's how low-key sound pressure waves are compared to like radiation and light energy delivery. Pretty crazy. Okay. So, weird thing is, I know I wrote parentheses. That's just because the problems look really messy. You don't have to put parentheses on here. Remember, you don't need secret parentheses if you're not dividing by scientific notation. This will just run straight through. And when we do it, okay. All right, that one little pocket, that one little moment burst of light, I'm going to give 1 decimal place because they didn't give me any. I'll say 1.3 times 10 to the negative 29th. Oh my god. And because you want that last half a point, that is joules because it is energy. Cool. That's it. That's the other energy equation. It's pretty low key. Just saying, what if? Okay, what if they asked for frequency? Okay, that means I got to get H out of the way. So if I needed frequency, that means, okay, instead of multiplying, I'm going to divide by H, so that'll move H to the other side and divide it. But we'll wait and see if that turns into a problem. I want to show you one more example before I throw a batch of them at you to let you fight with it. Okay. Let's go over here. Now, there's nothing that's mean about this, but I just want to show you kind of where the ceiling or the roof of this stuff is. So if I say boy. Sorry. Sorry, I realized the math is messy enough. I had to go proof it real quick. But we're back. Okay. So, I'm asking for what color? Will a 4.434 times 10 to the negative 19th joule quantum of light appear as? When I stretch it out, it's not that big or complex of a sentence. But what's going on behind it is really big. This is actually the meanest I could be with this. But that's why I'm going to walk you through it first. We're going to handle this together. So were you to see this, you could last it. Okay, but I know you're already firing and making connections. One thing, though, just to point out also, this word quantum, I know especially since Ant-Man, it's been getting a lot of, well, just popularity, notoriety, I don't know. The whole AU is kind of over. But at any rate, okay, so quantum. Quantum is truly just a name that we give these little bundles of light. That's about it. It's just a package. It's an amount. It's not an endless spectrum with a slider of energy. It means that every little shot and burst and wave and color has a predetermined amount of energy loaded into it, right? Because waves are energy delivery systems, so the quantum is just the package. So you're like, well, where is quantum mechanics and the quantum realm and everything? Okay. When you're that small and we're talking about packaging energy, the weird idea is waves are infinite. So the idea of a packages are very not infinite. They're very finite. So the concept is a lot of this really, it opens the gateway to some weird physics. But fortunately, that's not your problem yet. Hey, by the way, come back and take physics. No reason. So, joules lets you know that this sucker is energy. They didn't even use the word energy, but that's because knowing that energy is in joules, that's something you got to walk in with having memorized. When they say wavelength, you got to know you're looking for nanometers or meters. When they say frequency, that's a hertz or an inverse seconds, right? Disarming word problems is about knowing what makes numbers important, and it's not the numbers, it's the context. I don't care really what 4.434 times 10 to the negative 19th is, but when I'm like, oh shoot, that's joules, like, I care about that being energy, right? Because that means something. If I said dollars, now everybody cares, right? So context is what's important. So that's why units are super crazy important. Okay, let's do a little brainstorming here. Okay, they gave me an energy. When they ask for color, okay, these do not directly connect, right? There's no direct path from energy to color. But the closest thing we do have that does get us color is a wavelength, right? So if we can turn energy into wavelength, we can figure out color. But then when you go look over here at this equation, you're like, well, crap, there's no wavelength in it. But we can turn frequency into wavelength. This is the process that we're going to do on this guy, right? In the end, we're just going to go look at the color chart. But to do that, so color chart's going to show up here. But we need to do our first Planck equation. Then we're going to do our speed of light equation. Actually, write those in. That's a good idea. Once we do those, it's all good. Home free. So, let's start with part one. Let's get new out of here. Okay, energy 4.434 times 10 to the negative 19th equals Planck. And really weird to just be like, yeah, there's just this, aside from these completely sane numbers, is just a very reasonable looking V. But of course, none of this is sane and it's not a V. Okay, so ignore that this is just a giant, ridiculous number. I'm actually going to package it in so the scientific notation's contained and less scary. We need to move that off of nu, just like we did that from any other algebra equation. We're going to divide this off. As in, we're going to divide the whole Planck constant off underneath. Okay, when you do, you're going to get a number. want you to go ahead and test that out. Go ahead and give a pause. Slash, hey, I'm stalling while I hammer this out on my own in the background. Okay, and we're back. They're giving me lots of decimals. The longer you can hold off rounding, the better. So I'm going to take 4 decimals in this case. Still trying to do that extra one of precision that they seem to give us. Okay, hey, we got our inverse seconds here, or hertz if you want to. So it's about 6.7 times 10 to the 14th is the frequency. That's pretty intense. Okay, big numbers, big numbers. Okay, so that's part 1. Okay, part 2. We're going to use this frequency, and okay, that's the room we got to work with. We're going to use that frequency, and we're going to get lambda out of it, which means, hey, speed of light's back in the game. But since we're solving for lambda, I am going to move that around beforehand. So I'm going to divide off new. So this is the equation we're going to test out. Truthfully, I probably should have done that with up at the Planck equation, because it's so much easier to move letters than giant ridiculous numbers. Like, you know, it's the same thing we did, but hey, it would have been easier to write for the algebra. This is my public service announcement. Hey, move your equations while they're letters instead of numbers, because numbers are bigger and crazy. Speaking of, speed of light, 2.998 times 10 to the 8th meters per second. Frequency, I'm going to borrow what I got from the last guy. Okay, bigger numbers on the bottom, so I know this thing's coming out negative. Also, if I double check my units, the seconds are gone, which means meter is going to pop out. That's great, because I need a length. Lengths like meters, coincidentally. Okay, go ahead and pause while you do the calculator work. / ignore me typing away in the background. All right, here we go. Okay, after all this, totally worth it, no regrets. I'm going to round it off sooner than that, because I'm not just going to keep making it smaller and smaller. 4.48 times 10 to the negative 7th meters. If you did that, granted, and if you could do that on your own, you did some real work. But to make the color, you gotta go say what nano that is. All right, I'm just gonna do it right here. I don't even care. Let's nano this. So 7 hops to the left. 1, 2, 3, 1, 2, 3, 4, 4, 8. Yeah. Okay, so to nano it then, 3, 6, 9. This is the same as a much more user-friendly 448 nanometers. Of course, all 3 of these acceptable and truthfully the same. So let's go find 448 and call this thing good. Oh, God. 448. Need to sleep. Okay, that's kind of here-ish. Kind of right here in this border. 448. So yeah, this might be an indigo, kind of a deep blue bordering into purple slightly. So I'll say blue indigo. Sweet. All right. So you got 2 walkthroughs, which kind of gave you the once over. I'm going to make 3 practice problems. 3 practice problems. There you go. Okay. It's kind of a mix, a little bit of each. Don't really want to give much prompting. Go ahead and pause, because next thing I'm going to reveal the answers, but I'm not going to show off the work. I know. And there's your answers. All right, got your 2 colors on 1 and 3. Number 2 wasn't really a color question because we didn't go wavelength, but give them a shot. You got this. Bye.